We're going to end this lecture, lecture 10, by saying a few words about the Gibbs phase rule. All right, here is the Gibbs phase rule. It says that the degrees of freedom in a system is equal to the number of components in the system plus 2 minus the number of phases in the system. And remember from a previous part of this lecture, degrees of freedom are the number of components, the pressure and the temperature. We've talked about pressure and temperature for a single component, and in general you can have more than a single component. Determine a phase diagram for that, and therefore the number of components would also be a degree of freedom. And assumed, tacitly assumed in this, is that the volume is constant of your system. And the amount you have for pure substance doesn't really matter, but for composition of multi-component systems, you know that amount. So let's figure out how Gibbs got this relation. The degrees of freedom is components plus 2 minus phases. Just to refresh your memory, suppose we have a pressure-temperature diagram, and we have one component, and we say we just need just one phase. That means we can be anywhere in this plane. We have 2 degrees of freedom. We can vary independently temperature or pressure and get any point in this phase diagram. So for this particular case, the degrees of freedom will equal 2. Temperature and pressure. The degrees of freedom are temperature and pressure. Let's draw a part of the phase diagram here. These represent lines which are equilibrium between 2 phases. Now suppose we want 2 phases to coexist. In other words, we want it to be, say, at this temperature and this pressure. You have to be on this line. So if you specify temperature, you no longer have a degree of freedom for pressure. The pressure has to be that which will give you the point on the line. Or similarly, suppose you specify a pressure. If you want the 2 phases to coexist, it has to be on this line. So when you specify a particular pressure, you no longer have freedom to specify the temperature. It has to be that temperature which will give you this point on the line. So that if you increase the number of phases that you want at equilibrium, the degrees of freedom decrease. If you, say, make 2 phases, the degrees of freedom will decrease by 1. Let's sort of keep a running tab here. So degrees of freedom will equal, let's see, it'll be the minus the number of phases, because each time we add a phase, we decrease the degrees of freedom by 1. Now let's look at components. So far we've talked about a single component, but now let's go from, say, 1 component, now increase the number of components by 1 to go to 2-component system. For example, water and ethanol or something like that. So now we have 2 components. You would think by going to 2 components you would have maybe 2 more degrees of freedom. But that's not right, because the sum of the components has to equal the total amount in the system. For physical chemistry, as we had mentioned, we express concentrations in terms of mole fraction. The mole fractions of all the components have to equal 1. For 2 components, 1 has to equal the mole fraction of the first component plus the mole fraction of the second component. Because of this relation, you do not have independent control of both concentrations. For example, if you just specify a concentration x1, with that concentration x1, x2 has to be 1 minus x1. Because of this relation, you reduce your degrees of freedom from 2 to 1. Just like you reduce the degrees of freedom when you specify phases, because the chemical potential has to be equal on both phases, you reduce the number of phases by 1. So it seems each time you add a component, you'll increase the degrees of freedom by 1. So for instance, if you have 3, now you have 3 components. The 3-component mole fractions have to add to 1. So mole fraction 1 plus mole fraction 2 plus mole fraction 3 all have to equal to 1. But we can specify 2 of these, and then the third has to be calculated by this relationship. So when we went from 2 components, where we had just 1 additional degree of freedom, to 3 components, now we have 2 additional degrees of freedom. Looks like each time you add a component, you'll increase the degrees of freedom. And then there'd be some constant, let's call that constant B, which we can determine. In fact, let's determine that now. So we know that there are 2 degrees of freedom, when you have one phase and one component. This means that B, that constant term, is equal to 2. So the general Gibbs phase rule, degrees of freedom, is, I'll just write it, C minus P plus 2. So there's the Gibbs phase rule. It just says, well, if you're going to require phase equilibrium, two phases, you're going to have to reduce the degrees of freedom by 1 over just one phase. Or if you increase the number of components by 1, you increase the number of degrees of freedom by 1. And that's all there is to the Gibbs phase rule. That sort of makes sense like that. Gibbs phase rule. So that's it. Short lecture, last part of lecture 10. And now I'll go work on lecture 11.